press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about types of waves, that is transverse waves and longitudinal waves, right? Now, today we will discuss some more important concepts regarding the waves, right? Now, we will take some points as note. It is number one. So, in a transverse wave, a crest and a trough constitutes a single wave, or it is also called wave pulse. So a crest and a trough, right? That is called a single wave or wave pulse. Similarly, in a longitudinal wave, right, a compression and a rarefaction constitute a single wave or wave pulse. So here say compression and rarefaction that constitutes a single wave or single wave pulse. Now the third important thing is, right, so a wave motion is associated with two types of motions. We know that generally motions are classified into three types: translational motion, rotational motion and oscillational motion, right? Now, oscillational motion, which can be expressed in terms of cosine function or sine function, right, are called simple harmonic motions. Here, a wave motion, that means a motion of disturbance from one point to another point of the medium in the form of a wave, right, is associated with the two types of motion. One, right, the particles execute simple harmonic motion or vibration about their mean position, right? Number two, right, the translational motion of disturbance or energy from one point to another point in the direction of propagation of the wave, right? So we will take that one. So third one, a wave motion is associated with number one, a simple harmonic motion of particles of medium about their mean position. This is number one. Number 2, translational motion of disturbance or energy in the direction of propagation of wave. Therefore, here we are associated with both angular quantities like angular frequency and linear quantity like linear velocity. But when we speak about velocity and acceleration, right, particularly, now these simple harmonic motion executing particles have velocity of simple harmonic motion, right? It is maximum at mean position and zero at extreme position. And acceleration of simple harmonic motion, it is maximum at mean position, maximum at extreme position and zero at mean position, right? But here again the disturbance or wave motion has a velocity, and that is called as a wave velocity. Here we should not get confused. The velocity of particle means it is the velocity of simple harmonic motion about its mean position, and it varies from position to position. But the wave velocity is the velocity of the disturbance or energy, right? That is usually a constant or uniform velocity in a homogeneous medium, and these things have to be keep in mind. Now, the fourth, what is the function of a wave? Right? The function of a wave is to transfer energy from one place of the medium to another place without transferring matter, and that is important. We know that there are two types of transportation of energy. One, right, particle motion, where both matter and energy are transferred. For example, a bullet fired from a gun. Second type is wave motion, where energy is transferred but matter is not transferred, right? So wave motion is very important because it transfers only energy but not matter, right? So a wave transfers energy from one point or place to another point of a medium without transferring matter. So this fact makes the waves and wave motion are very important to study, right? So with these points we will move towards another concepts. Right. Now, as wave motion involves both simple harmonic motion of particle as well as translational motion of disturbance in the direction of propagation of wave. Right. Now, here waves can be understood in terms of some basic terms like amplitude, period, frequency, wavelength, wave velocity, phase, etc. Right? So let us define. We have already defined amplitude, frequency, time period for a simple harmonic motion, right? But now we will define some terms regarding to the wave. Remember that in the previous chapter, when we were discussing simple harmonic motion, it is a single particle executing simple harmonic motion. But when we are talking of wave motion, a large number of particles of material medium, that means atoms or molecules, they execute simple harmonic motion, right? Remember, one, there is a simple harmonic motion of particles, right? Number two, translational motion of disturbance or energy, right? So we'll take some basic terms which will help us understanding waves and wave motion, right? Now the first term we are going to discuss is wave amplitude. Again, it is denoted by the symbol capital A. Wave amplitude or amplitude of a wave, right, is the maximum displacement of the particles, right, executing simple harmonic motion in the medium on either side of its mean position, right? So wave amplitude is equal to maximum displacement of particles of medium executing simple harmonic motion from their mean position, right? So in simple harmonic motion alone, there is only one particle executing oscillation, but here large number of particles are executing oscillation. And of course, when a wave propagates through a medium, all the particles vibrate with the same period, same frequency and same amplitude. Therefore, amplitude of one particle is same as the amplitude of all the particles of the medium and is called wave amplitude. Number two, it is wave period, that is T. Wave period, right, of a wave propagating through a medium is the time taken by the particles of the medium executing simple harmonic motion to complete one simple harmonic motion or one oscillation or one vibration. Generally, here, right, the frequency of simple harmonic motion is higher. Therefore, generally we take vibration, right? So, if frequency of simple harmonic motion is low, then generally we call it as oscillation. That is oscillation of a simple pendulum, oscillation of a loaded spring. When the frequency of simple harmonic motion is high, right, then we will say vibration, right? We call it as vibration of a tuning fork, vibration of a stretcher string. Both are simple harmonic motions, but the word oscillation is used when frequency of simple harmonic motion is low, and the word vibration is used when frequency of simple harmonic motion is high, right? So here we are using that word vibration, right? It is clear that wave period is equal to time taken by particles of the medium to complete one vibration. It is denoted by capital T and measured in seconds. It is in general. But again, we have alternate definition, right? So, wave period of a wave is the time interval during which one single wave is generated or one complete wave is generated. That is, wave period is also equal to time interval during which, right, one complete wave is set up in the medium. That means here, when we are having a transverse wave, so the first particle, say at O, starts vibrating under the action of deformation force. Now the vibration is transferred to next particle, and so on. So when this one complete wave, compression and crest and trough are formed, then the time taken is equal to T. Similarly, when a longitudinal wave is propagating through a medium, the time taken to generate one complete longitudinal wave, that is one compression and one rarefaction, is equal to time period. Obviously, both definition will give the same time period. Suppose if the time period of vibration or time taken by particles of propagating medium to complete one vibration is 2 seconds, then it takes 2 seconds to generate a complete wave. That is, in case of transverse wave, a crest and a successive trough, and in case of longitudinal wave, a compression and a successive rarefaction, right? So these alternate definitions will help us in better understanding waves and wave motion, right? Is it clear? So number 3, wave frequency, again denoted by the symbol F. Now, wave frequency or frequency of a wave propagating through a medium, right, is the number of vibrations completed by the particles of the medium in 1 second, right? That means wave frequency is equal to number of vibrations completed by particles of medium in 1 second, right? Generally, all particles of propagating medium vibrate with the same frequency and same period. Now, again, we have an alternative definition, and this is very important, right? So, wave frequency or frequency of a wave propagating through a medium is the number of waves passing through a fixed point in a medium in 1 second. Now, wave frequency is equal to, it is the number of waves right, passing through a fixed point in medium in 1 second, or it is also the number of waves generated in the medium in 1 second. We know that single wave or wave pulse, right, consists of one crest and one trough, one compression and one rarefaction. Suppose if I am having a tuning fork of a frequency say 100 Hz, the tuning fork is vibrating with a frequency of 100 Hz. For one to and fro motion, one vibration of the tuning fork, it constitutes one compression and one rarefaction, right? So at any point we take here the point P here, so 100 waves, right, pass in 1 second. That means alternate 100 compressions and rarefactions pass through this fixed point. Or this tuning fork generates 100 waves per second. In 2 seconds, 200 waves. In 3 seconds, 300 waves, etc. Suppose if its frequency is some 400 Hz, then the number of longitudinal waves generated per second is 400, or the number of longitudinal waves, right? One longitudinal wave means it is a compression and rarefaction. The number of, right, longitudinal waves passing any fixed point in the medium is 400 waves per second, right? So you might have seen the definition. So this definition is regarding simple harmonic motion, and this definition is regarding wave motion, right? So frequency of a wave is the number of waves generated in a medium per second, or it is the number of waves passing through a fixed point in the medium per second, right? And of course it is measured in hertz, that is SI unit of frequency is hertz. Now the fourth and important term, right, first time we are using in the study of oscillation and waves. It is wavelength of wave, denoted by the symbol lambda. Lambda is a Greek alphabet, just like alpha, beta, gamma, theta, delta, etc. The standard symbol for the wavelength of wave, any wave, is lambda. And one more thing, in general, we are having two types of waves in our day-to-day life: mechanical waves and electromagnetic waves. So when we are dealing with mechanical waves, frequency of wave is generally represented by the symbol, right, F, right? Sometimes it is also represented by the symbol small n, that is for mechanical wave. But as far as electromagnetic wave is concerned, the frequency is denoted by the symbol nu. Remember that the formula, Planck's law, E is equal to h nu, where nu is the frequency of radiation or light, which is an electromagnetic wave. But lambda is the symbol used generally for both electromagnetic waves and mechanical waves. Right. Now, coming back to this wavelength of wave. Right. Now, there are several definitions for wavelength of wave, which we use in various situations, right, to derive some relation or to understand some concept. Now, the main definition of this wavelength is that, right, wavelength of a wave is the distance between, right, the two particles of the medium, distance between two consecutive particles of the medium which are in the same state of vibration or phase. Right. Now remember the term we have discussed in discussing oscillation, that is phase of a particle executing simple harmonic motion. Phase of a particle at any instant of time is the state of vibration of the particle at that instant of time, right? And it represents both position of the particle from the mean position and direction of motion of the particle with respect to the mean position at that instant of time. And it is expressed as the fraction of time period or fraction of the angle 2π. Right? So here definition number 1. So wavelength of a wave is the distance between two successive or consecutive particles of propagating medium which are in same state of vibration, which are in same state of vibration, right? For example, let us consider a transverse wave propagating through a medium. We know that a transverse wave consists of, right, alternate crests and troughs, or a series of alternate crests and troughs. So here there are different particles. They say particle at O, another particle at A, particle B, C, D, E, F, right, G, H, etc. Right? So number of particles. So the second particle begins to vibrate little later than the first particle. The third particle, right, begins to vibrate little later than the second particle, and so on. So different particles of the medium are set into vibration at different instant of time. Therefore, the different particles will have different phases. Now we see the particle at O and the particle at D are in the same state of vibration, right? Their position, they are in the mean position. Displacement y is equal to 0. And the next moment they start moving in positive direction. So the distance between O and D, right, is called wavelength of the wave. Again, we take the particles A and E. These two particles, right, are in the same state of vibration or phase, because it is the position is in maximum, right, displacement position in positive direction. This is also maximum displacement position in, right, positive direction. So therefore, both of them have same position and same direction of motion. Therefore, the distance between these two particles A and E is also equal to wavelength of wave. Then we see that the particle C and particle G, again they are in same state of vibration, having maximum displacement in a negative direction and the same direction of motion. So here O and D are two successive particles in same state of vibration. A and E are another set of particles, two successive particles or nearest particle which are in the same state of vibration. So here also C and G are the particles which are in the same state of vibration. So wavelength of a wave is the distance between two successive particles of propagating medium which are in the same state of vibration. Now see, this is crest, this is trough, this is crest, this is trough. See, what is the distance between A and E? Equal to lambda, right? A and E are two consecutive crests of a transverse wave. Their distance is equal to wavelength. See here, the distance between two successive troughs in a transverse wave, it is also equal to wavelength of wave. Can I give another definition, an alternate definition? In case of a transverse wave, wavelength of a wave is the distance between two consecutive crests or two consecutive troughs, right? And that is the another definition for wavelength, right? Similarly, I can say that. What about in case of, right, longitudinal wave? In case of a longitudinal wave, right, crest can be compared to compression and trough can be compared to rarefaction. Therefore, in case of, right, a longitudinal wave, right, wavelength of wave is the distance between two successive compressions and two successive rarefactions. Is that clear? Wavelength of wave. Now we will take alternate definitions of this wavelength of wave. So now we are having A. I can take no. So in a transverse wave, wavelength of wave is the distance between two crests or troughs. So again, the same diagram we can take. So here, this is crest, trough. So this distance is wavelength and distance is wavelength, right? So you could take anything, but we have to take only two consecutive crests and two consecutive troughs whose distance is equal to wavelength of the wave, right? Now, it is an additional information I am taking here. So, the distance between, from figure, the distance between a crest and an immediate trough is equal to half of the wavelength. And again, the distance between a trough and an immediate crest is lambda by 2. It is an additional information. You remember that the distance between a crest and an immediate trough is half of the wavelength. Similarly, the distance between a trough and an immediate crest is equal to lambda by 2, right? Is that clear? Now B, in a longitudinal wave, wavelength is the distance between two consecutive compressions or rearrangements. Now, let us consider a longitudinal wave consisting of a series of alternate compressions and rarefactions. See here, this is compression, rarefaction, right? Compression, rarefaction, compression. Here, the distance between two consecutive compressions is equal to wavelength, and the distance between two consecutive rarefactions is also equal to wavelength, and of course, distance between a compression and an immediate rarefaction is lambda by half the wavelength, and distance between a rarefaction and an immediate compression is equal to lambda by 2, right? So this is another alternate definition for wavelength. Now C, right? Here, wavelength of a wave is the distance traveled by the wave, right, in a time interval equal to its speed. Wavelength is equal to the distance traveled by the wave, right, in a time interval equal to its period. Right. Now, for example, we'll take now when we disturb a particle at O in a medium, it began to vibrate. It transfers its vibration to the second particle, second to third, third to fourth. Now, different particles of the medium, right, are vibrating about their mean position, right? When this particle completes one vibration, the first particle, right? Now, the time taken T is equal to T, right? Now, the disturbance has moved from O to the position A. So, after a time interval equal to its period, now the wave has traveled from O to A. So, this distance O to A is equal to wavelength, right? So, wavelength of a wave is also equal to the distance traveled by the wave or disturbance, right, in a time interval equal to its time period, right? So remember that what we have discussed while discussing wave period, right? Wave period or period of a wave is, right, the time taken by the wave, time taken to complete, right, or to generate one complete wave, right? So the time period is equal to time taken to generate one complete wave. Now the O and A are in the same state of vibration, right? So in a time interval T, right, the wave or disturbance has traveled from O to A through a distance lambda. So the distance traveled by the wave, right, S is equal to lambda in a time interval T is equal to T. And also we see that what is this OA? OA is a wave pulse or a single wave consisting of crest and drum. So wavelength of a wave is also the time term. Wavelength of a wave is also, right, the length of a single wave. Right. So D, right, wavelength is also equal to length of a single wave, that is equal to the length of, right, successive crest and complete one transverse wave, or it is equal to the length of one longitudinal wave, right? That is another definition. So wavelength has different alternate definitions. These different alternate definitions help us in understanding, right, the what we call the concepts of waves. Now, the fifth one, it is wave velocity denoted by V. Again, I would like to remember you, wave motion is associated with two motions. Simple harmonic motion of particles about their mean position, where velocity of simple harmonic motion is sometimes called as particle velocity, is not a constant velocity. It varies with the position of the particle. It is maximum at mean position and minimum at extreme position. But here we are talking about the velocity of the wave, that means the velocity with which the disturbance moves through propagating medium. Now, this wave velocity of a wave, right, or velocity of a wave is defined as the distance travelled by the wave in a time interval equal to 1 second. So, wave velocity is equal to distance travelled by wave or a disturbance in 1 second, right? So, in wave motion, two velocities are associated. Velocity of simple harmonic motion, right, that varies with respect to time, right? That velocity of simple harmonic motion, right, is V is equal to omega into square root of E square minus Y square. This is the velocity with which particles of the medium execute, right, simple harmonic motion, right? But wave velocity, right, is a uniform velocity. In a homogeneous medium, velocity of wave is a uniform velocity, right? It does not change with respect to time. Since there is a change in velocity of simple harmonic motion, it is associated with acceleration. But since there is no change in velocity of a wave, it is not associated with the acceleration, right? Particularly, remember that in a homogeneous medium, a wave travels with the constant or uniform velocity called wave velocity. It is the distance travelled by, right, the disturbance or wave in the direction of propagation in 1 second, right? Is that clear? Now the sixth one, it is phase, represented by the standard symbol phi. Now we have discussed about the phase in simple harmonic motion, that is oscillation. Phase of a particle executing simple harmonic motion, that is oscillation or vibration, at any instant of time, is the state of vibration of the particle at that instant of time. The phase of a vibrating particle at any instant of time, right, gives both position and, right, state of, right, direction of motion at that instant of time. Now that means we have phase of a vibrating particle at any instant of time is the state of vibration of the particle at that instant of time. At that instant of time. Right? Now, state of vibration at any instant of time represents both position and direction of vibrating particle at that instant of time. So the state of vibration represents or gives both position of the particle from the mean position and direction of motion of the particle, right, with respect to the mean position at that instant of time. Now this phase phi is expressed in terms of fraction of time period t or fraction of angle 2 pi. It is expressed in terms of fraction of time period t or fraction of angle. Now phase of a vibrating particle at any instant of time is the time interval during which the particle last crosses its mean position in positive x direction, or phase of a vibrating particle at any instant of time is the fraction of time period that has been elapsed since the particle last crosses its mean position in positive direction. So the phase is expressed either in terms of fraction of time period or in terms of fraction of 2 pi. Now, let us consider a wave propagating through a medium, right? That wave can be represented by plotting a graph of displacement against time. Let O be the origin when we take the Cartesian coordinate system for first particle of the medium, which is disturbed. So when a wave propagates through a medium, say a transverse wave, it propagates in the form of a series of alternate compressions and alternate crests and troughs. Here we have a particle at A, particle at B, particle at C, particle at D, particle at E, particle at F, and so on. There are a number of particles. All the particles are vibrating, right, about their mean position, but phase of different particle is different at any given instant of time. So we will take phase of different particles. So in a wave, now phase of particle at O. Right. Since the particle is at the origin in the mean position, the phase difference, angle covered, is 0 or time taken t is equal to 0. So here the phase is 0. Now phase of particle at A, here phi is equal to pi by 2 because it has covered an angle of 90 degree, or the time taken is equal to t by 4. You see the definition? Phase of a vibrating particle at any instant of time is the time period, the fraction of time period that has been elapsed since the particle last crosses its mean position in positive direction. So the particle or the disturbance right now started from O to reach at that point, right? The disturbance to reach at that point, the time taken is equal to T by 4, or in terms of angle it is pi by 2. Similarly, phase at B, phi is equal to, here this is T by 2 or pi. Phase is pi or T is equal to T by 2. Now phase at C, phi is equal at this point. It is in terms of time period 3 T by 4 or 2 pi by 3. That means 270 degree. 2 pi by 3, 270 degree. 3 pi by 2. 2 pi by 3. 2 pi by 3 means it is 360 degree divided by 3. Now this is I think it is 3 pi by 2. This is 3 pi by 2 or T is equal to 3T by 4. Similarly, phase at D, in terms of fraction of time period it is T, and in terms of angle it is 2 pi. So here phi is equal to 2 pi or T is equal to T by T, capital T. So phase of the particle at A is T by 4 or pi by 2. Phase of the particle at B is T by 2 or pi. Phase at C 3T by 4 or 3 pi by 2. Now here this is phase at D is T and it is 2 pi, right? Now one thing we have to be aware, when the particles are vibrating and wave is propagating through the medium, at any given instant of time t, different particles are vibrating in different states of vibration or different phase, right? Now that's all about the fun. So here the phases for different particle is different at any given instant of time. Right? So far we have discussed about the basic terms in this class, starting from wave amplitude, wave period, wave frequency, right? Wavelength, wave velocity, and the term phase, right? Is that clear? So thank you very much. We will continue in the next class.